We're going to start today's lecture with the concept of an equalizer. Have you seen the movie called Equalizer? With Denzel Washington, he makes things fair.
But I'm in the categorical algebra short course, so touched on.
Okay, that's great. So I'm going to start with the definition, and then we're going to make sense of the concept by looking at various examples. If I have two morphisms in a category, F and G, which might be different from each other, I want to have a way of identifying how different are they from each other. And that is done through a morphism that goes into X, which we'll later call equalizer of F and G. This morphism should obey the rule that FE equals GE, and also it should have a universal property for this rule, which will be similar to the universal property for the product of two objects. So if I have another morphism E prime with a similar property that FE prime equals GE prime, then I would like there to be a unique morphism E prime, unique morphism from E prime to E, let's call it H, such that the triangle there commutes. In other words, E prime equals EH. So let's write this out. An equalizer of F and G, and this notion is only defined for morphisms that are parallel to each other, which means that they have the same domain and the same codomain. An equalizer of F and G is a morphism E such that firstly it holds that F equals GE, and also for any morphism E prime having the property that Fe prime equals GE prime, we must have a unique morphism H such that EH equals E prime. Let's immediately look at the category sets. Let's say F and G are some functions from a set X to a set Y. And now we're looking for, let's first try to find functions from E to X such that Fe will equal GE. And among them, we will want to choose the terminal one, the one that has a unique morphism going into from any other. So you can actually organize these morphisms into a category, the ones that satisfy this equality of F equaling GE. And in this category, you're looking for eternal options. Let us do this on a specific example. We'll draw two specific sets, maybe not very specific, at least they will be specific enough that we'll have a picture for them. And then two functions between them, and then we'll look for all possible e's. So let's say the first set has 4 elements, and let's say the second set has 3 elements, and F is an orange mapping. So this is what F does. And G will be blue mapping. So let's say G takes this one there, that one it takes there, this one it also takes there, and finally the last one it takes there. And just so that we don't give impression that jointly F and G exhaust all of the codomain, let's also add a few points in the codomain that are not being mapped to. So the orange arrows indicate the function F, and the blue ones indicate the function G. Now, let's construct some examples of functions into X. So this is our X here, right? That's Y. Let's construct some set. Let's call it E1. Let's actually do three of them, one for each. I'll name one example, and then each of you can name an example as well. Let's just label the elements of X and Y so it will be easier to refer to them. I'm going to call these 1, 2, 3, 4. And the ones in Y, I'm going to call them again 1, 2, 3, 4, and 5. So, Carlisle, would you like to give an example of a function of a set? First of all, you need to name a set E1, and then a function from E1 to X that will satisfy the property that will be called, function will be called small e1, and we want from this function that f e1 equals ge1.
You just take the singleton 2.
So first of all, you need to describe the set e1, right?
Yeah, singleton 2.
It's a singleton set. Okay. You want its element to be called 2.
Yeah.
Mm-hmm.
Sorry. I was implicitly looking for subsets. But yeah. And then it should say 2 to 2.
And you're mapping 2 to 2. Yeah. Okay. Michaela, do you agree that for this function f e1 will equal ge1?
Yes.
Mm-hmm. So if I want to write this out explicitly, f e1 of 2 equals f of 2, and that equals 3, whereas g e1 of 2 equals g of 2, and that happens to also equal 3. So the two functions are equal since 2 is the only element in the domain e1. Great. Would you like to go next?
What if E2 is X itself and we have the identity mapping? So if lowercase e2 is the identity map.
Okay, let's try that. So everything maps to itself, right?
Sorry, that's not going to work.
Is it not going to work? Okay.
No, sorry.
That's fine. So let's just let me just explain why it's not going to work for anyone else who's listening to this and is not sure. For instance, it's not going to work because if I start with 1 here, I map it to 1, then the blue arrow and the orange arrow take that one to different places. It's no longer the case that FE1, well, FE2 will equal GE2. Sorry, FE2 will not longer equal to GE2. Would you like to give another try?
Yeah, okay. So I think if you have a E2 is a 2-element set, and then you map the first element to 2 and the second element to 4.
Would you like to give names to these 2 elements before we map them?
We can call them 1 and 2. I think that'll.
Let's call them 1 and 2. And 1 is being mapped to 2.
Yeah.
And 2 is being 4.
Yes.
Okay, that's great. Now this map is called E2, and we can check that the requirement holds here. FE2 equals GE2. Instead of writing it out algebraically like we did here, let's just trace the arrows there. So 1 maps there, then by F it goes to 3, but by G it also goes to 3. So as far as the element 1 is concerned, it's fine. And then for 2, 2 goes here, and then by G it goes to 5, but by F it also goes to 5. Sorry, the other way around. But both of them take this element to 5. And so since the 2 composites are equal for the elements 1 and 2, they're equal throughout because 1 and 2 are the only elements of the domain of the composite capital E2. Great. Okay, now it's my turn. Let me name a third example. So this will be E3. I deleted something extra, no, I didn't. So E3, so my E3 is going to look like this. I'm going to have E3 equal to the set of natural numbers. So it's going to be an infinite set. And I'm going to partition this infinite set into 2 pieces, even numbers and odd numbers. And then I'm going to plagiarize what Michaela told us. I'm going to send all the odd numbers where 1 was sent to by the previous map. So all of the odd numbers will be sent to the 2 over there. And I'm going to send all the even numbers where 2 was being sent to previous time, which will be 4. Do we still agree that the composites FE3, GE3 will equal? Do you agree with that as well, Michaela?
Yes.
Fantastic. Now let's see if any of these happen to be an equalizer of F and G. We can start with E1. Let's see whether E1 is possibly an equalizer. If it were an equalizer, well, the first part of the definition is fulfilled. The first part that requires the composites to be equal. That part is fine. But there is a second part that any other such map must factorize through this one uniquely by unique age. And we've got a few others like that. For instance, we've got E2, that's also like that. So if E1 is an equalizer, there must be a unique function from E2 to E1 such that the composite with E1 equals small e2. Does such H exist? Or, and maybe if it exists, then is it unique? So you said no, Caroline. Would you like to explain why not?
So it's any morphism will be unique because there's only one element in the codomain, but it won't commute.
So you're saying that E1 only has one element, so there is only one function from E2 to E1. So uniqueness part will be fulfilled, but we just want to make sure the existence part is also fulfilled, yes?
But it won't be because or nothing in E1 goes to.
Right, so we will have a trouble deciding where to map to. If I map 2 to 2, which is the only place I can map it to, then after that, E1 will map it to 2 again, but that composite going there and then going here must match with what small e2 does, which maps to 4. And as we see from the picture, there is no match because in one case we get number 2, in the other case we get number 4. Fantastic. Are you happy with that explanation, Michaela?
Yes. Yes.
So we now decided that E1 can't be an equalizer. Okay, I'm now going to ask whether E3 is an equalizer. Again, the first part is fulfilled, FE3 equals G3. And if it is an equalizer, then from any other such map, there must be a unique function going to capital E3, making the triangle commutative. So let's pick the other one this time. Will there be a unique function going this way? Shall we first decide whether it exists or whether it's unique? Which one shall we decide first?
We've already talked about uniqueness of the elements.
Well, we can argue like before. You were arguing that there must be unique, or rather at most one.
Yeah, okay.
Yeah, so that's what I meant. So shall we decide whether it's at most one or at least one first?
There's at least one.
There is at least one, you say.
Yeah, I mean at least one map H from E1 to E3. Is that what we're trying to argue?
Okay, let's look at that first. If there is at least one map such that E3 composed with that map equals E1. So do you think there is at least one such H?
Yes, I mean there is at least one. You could take 2 and map it to any odd number, and then
Right.
the number would map back to 2.
Right. But now you said any odd number, and it makes me think. So there's probably many of them, right? Because we can map 2 to any odd number, and there are many odd numbers.
Yes.
So we also have the answer for uniqueness, that it's not unique. There are many of them. So neither E3 is an equalizer. And of course, checking that something doesn't hold, for that it's sufficient to have a counterexample. When we will be at the stage when we want to prove that something is an equalizer, just working with these three examples won't be enough. E2, could E2 possibly be an equalizer? What does your intuition tell you?
Yes.
Okay. So let's prove that E2 is an equalizer, working with not just E1 and E3 specifically, but with a general E. Because if I want to establish a positive statement, then I need to prove it for all values that go under the quantifier, right? We're quantifying here over arbitrary maps going into X such that F that map equals G that map. So let's take an arbitrary E and some arbitrary function E. And now we want to prove that there exists a unique. Of course, we know from E that Fe equals Ge. We're not just taking any map, we're taking any map that satisfies that property as per definition. That's all we need to do. And then for that map E, we need to check that there exists a unique H from E to E2. Okay, let's maybe first establish existence of H. So if I pick an element X in E, I need to decide where I should map this to. Where shall we map that element to?
X needs to go to either 2 or 4 through E.
The small e, Carla, you're saying that the small e will map this X to necessarily either 2 or 4. It can't map it anywhere else. And I think I agree, because if it does map X to somewhere else, either to 1 or 3, let's say, then F and G will separate them. So F and G will separate where 1 or 3 further maps to. And so then F equals G will not be fulfilled anymore. Do you agree with that argument, Michaela, that X must be mapping, E must be mapping X either to 2 or 4?
Yes, yes.
And so we have 2 cases where E of X is, first case is when E of X is 2, and the second case is when E of X is 4. That's the only cases we have. And then I guess in the first case, we would want H of X to be equal to 1. And in the second case, we would want it to be equal to 2, right? So that then the triangle commutes, in other words, so that we have E2H equaling E. This is actually something we were forced to do according to this equality, weren't we? So we not only have now that the H exists, which we built one, but also that it's unique, because it must be this in order for E2H to equal E. Do you agree with that, Michaela?
Yes, yes, I do.
So it seems like we proved that your choice of the map, Michaela, is actually an equalizer, E2, in this specific example. And this gives rise to 2 questions in our exploration of the concept. What are these 2 questions?
We're supposed to give suggestions, but
Yeah, so there are two very natural questions coming out from this investigation. What are we trying to do here? We're trying to understand the concept of an equalizer. We build an example of an equalizer. We proved that in this example, the map we have is actually an equalizer. But now, in our further exploration of the concept of equalizer, based on what there are 2 questions that are arising.
Can I?
Yes.
So I think the first question would be, how did we decide what the set E2 was? And then how did we decide what the mapping E2 was?
Okay, so your questions are even more fundamental than what I was what I had in my mind. Your questions will then, answering your questions will then also be able to answer the questions I had in mind, which were how do we generalize this? What are equalizers in general? That's one question. And the second question I had in mind was whether this is the only choice in this example, whether maybe there is another equalizer as well.
I was thinking that
That's a good thought. Is the equalizer function always injective? That's another question that comes up here, because in this example it seems to be injective. So how did we, let's answer your questions, Michael. How did we decide on E2, capital E2 and small e2? How did you decide on them?
So it was looking at where do F and G sort of align. I think that's what I did. So looking at where does where do F and G map the same elements to one another, and then how many of them were there. And then what? Sorry, what's the second part? Well, to decide on how many elements to put in the set, how many elements, or how many elements were F and G aligned on. Right. So you seem to be suggesting something very, very general. If I have now 2 abstract sets X and Y and 2 functions F and G between them, you seem to be suggesting that we propose as a potential equalizer, we propose the set E. Okay, let me actually use the notation, the standard notation for this.
sometimes write equalizer this way. EQ with capital E for the object and with small e for the arrow. And so there is a suggestion to make EQ of FG to be those elements of X such that, as you said, F and G align. So F of X equals G of X. Do you agree? Did I capture your idea correctly here?
Yes, yes.
Interestingly, though, that's not what you did here because you renamed these elements.
Yes, I think I sort of, I tend to always start labeling with 1 and 2. I mean, that's
yeah. But we must be reminded of the phenomenon that we already saw for products, that when we define things in a category, they are unique only up to isomorphisms. In the case of the category of sets, it's uniqueness up to bijections. So it's okay to provide another equalizer, which we did in this other example, in this first example, that's a different set as long as it's bijective to this one. And that will be then actually describing all possible equalizers. So take this or any set bijective to this. Let's write this actually. Or any set bijective to the one above, right? And maybe now we are ready to test the validity of this being an equalizer in the general case. So if I have now a set E and a function E, small e, I could argue that because Fe must equal Ge, of course that's not true for any E, but we pick small e in such a way that it is true. So since they're equal, it implies that the image of E, all the values to which things from capital E get mapped to, must be entirely contained into the thing we built. Do we agree on this?
Yes. No, actually, I probably do, but I haven't worked around it yet.
So I pick an individual element here, I map it somewhere, and because Fe must equal Ge, that somewhere must be mapping to the same spot by both maps.
Yes. Okay.
So that means, yeah, that means that somewhere falls in the set we pointed out.
Yes.
Okay, great. I'm just rewinding back a little bit, take these extra things off. I'm going to put this part in brackets here because the subset inclusion will no longer be true if I picked a bijective set. But now that we know that the image of E is a subset of the equalizer of F and G, and also this map being a subset inclusion, we do have it. There's only one way to go here, which is just to map every X to itself, isn't it?
Yes, yes.
There can't be another way. As soon as X is mapped to something else, it's going to map to itself by this map, and then it will not match with the value that E has, right?
Mm-hmm. Yes.
Yeah, I actually lied to you, and you believed me kindly. What we want to write here is that X maps to E of X. Yes.
Okay.
The coincidence of elements happens at this level, not at this level.
Sorry, the what of elements?
The coincidence of elements. So X maps here to E of X, right?
Yes.
Now there yeah, there it should map somewhere so that when we insert it back into X, it is E of X, but there's only one thing that it inserted back gives it EX, it's E of X, EX itself, huh?
Yes.
Great. So we built an equalizer for arbitrary F and G. And now we could try to show that any other equalizer will actually be of this form up to bijection. But we don't need to show this on the example because we have a general result that any two terminal objects coincide. So let's first rephrase this problem in the language of finding a terminal object. An equalizer of F and G is a terminal object in the following category. Objects of this category are such diagrams. Maps E such that FE equals G, these are the objects. So in other words, if I want to be a bit more set theoretically formal, then I will say that objects are pairs. In other words, objects are pairs, capital E, small e, such that small e is a morphism from capital E to X and FE equals G. So these are the objects of the category. Morphisms are commutative triangles. So if I have two objects, then a morphism is exactly the thing we want to be unique. So a morphism from one pair to another is a morphism H from E to E prime, such that EH equals E prime. Are we good with how the objects and morphisms are defined?
Yes.
And finally, we also want to define composition. So if now I have three objects, and two morphisms between them, let's say H and H prime, we will define their composite, the composite of H and H prime, to be their usual composite as morphisms between running from E double prime to E. But there is one thing we need to double check. What do we need to double check for this composite in order for this to be valid composition in the category we're building? Yeah, that this requirement still holds for that composite. So in order for, let me first write this out in the language of pairs. So if I have H from E to E prime, and I have H prime from there to E double prime, I'm now claiming that I'm going to have a morphism, which is the usual composite H prime composed with H, but I'm claiming it's going to be a morphism from EE to E double prime. And for that claim to be true, I need to check the requirement of morphisms, which one of them is the triangular picture, which in this case is fine. We've got a triangle, but furthermore, this triangle must commute. So I want E composed with, on the other side, sorry, I want E composed with this composite to equal E double prime. Do you agree with that, Michaela?
Yes.
And let's see if this is so or not. E composed with this composite by associativity is the same as E composed with H and then composed with H prime. But E composed with H, because H is a morphism, is equal to E prime. And we get this. And E prime composed with H prime, because H prime is a morphism, is equal to E double prime. Is that okay?
Yes, I agree.
We can also trace this algebraic computation on the diagram. I want this path to be the same as this one. And to establish that, I notice that this path can be decomposed into, rerouted into this path, because this is the same as that. And then this path can be rerouted to that one. And then we're done. So just by looking at these diagrams, one can establish equations of arrows. One doesn't have to write out the algebraic computations here. And one of the tools of category theory that's actually useful in some cases, outside mathematics even, specifically in physics, they use a bit more sophisticated version of this to represent some complex algebraic arguments in a geometric way.
Is there, if you're working with like a very big diagram, and you have like commutative triangles or squares, things all over, is there sort of a simple algorithm that tells you, okay, this quadrant can shift down there?
Yeah. So if you've got a diagram, a big diagram that's made out of pieces, a little side question here. If I've got a big diagram that's made out of pieces, right? And if each piece commutes, then the big diagram also commutes. But one has to correctly define what pieces mean. So these pieces need to have, of course, overlaps. So on the boundary of each piece, there's a common arrow. And we'll use this a lot in practice. It's quite obvious on each individual example. So one doesn't actually formulate this as a formal theorem, but one could if one wanted to.
I wonder how you formulate it if you have non-finite number of pieces.
If you have non-finite number of pieces, then you can't compose things because you can only define the composites. Okay, we've built composition, but we don't know yet that it's associative. And here we will say that because this composition in this category is defined via underlying composition in the starting category, and there it is associative, so here it's obviously will be associative as well. The associativity equation will not change here. And the same holds for identity morphisms. There will be identity morphisms for this category, since if I have the same object twice, then the identity morphism of the original category will work. Is that clear for you, Michaela?
Yes.
That will serve as the identity morphism. I don't have to specify what identities are as part of the structure, because as we know, they can only be chosen in a unique way. We proved this, I think, right at the beginning. But of course, composition could have been chosen in various different ways, so that I have to specify. Okay, so now in this category, a terminal object is what? It's an object such that for any other object, there is a unique arrow. And this is exactly our definition of an equalizer, right? Do you agree with that, Michaela?
Yes. Yes.
Both conditions of equalizer are here. This one and this one. The conditions we were requiring for H is here, and the one we were requiring for any other in order to produce the H is also there, because this E prime must be an object, so it must fulfill something similar to that. And now we can say that equalizer is actually a terminal object in this category. Why do we want to do that? Because then as a next step, we can apply the general theorem that any two terminal objects are isomorphic to each other. And moreover, once I have one terminal object, I can describe all the others as objects that are isomorphic to this one. And so I just need to compute in this case what that means. So what will be isomorphic objects to a specific equalizer which we've chosen here? We've chosen a specific equalizer here. And now by the terminal object argument, we can describe all the others. So by the terminal object argument, all other equalizers of F and G in the category of sets are given by. So let's draw the picture for our chosen equalizer. We want to compute what are isomorphic objects to this one. So what are other things, other objects? Obviously, they will satisfy the FEG condition, which are isomorphic to this one. And isomorphism in that category means that there is H this way, and there is H the other way. And these two H's are inverses in that category. But because composition in that category is computed the same way as in the original category, it means that there are inverses in the category of sets. So we already spoke of the identity morphisms in this category being just identity morphisms of the domains of those arrows. So we want these composites in both directions to be either one or the other identity arrow. But that simply means that we want H prime H to be usual identity of E, and H prime to be usual identity of equalizer F and G. And in the category of sets, it just means that H and H prime are bijections that are inverses of each other. Okay. So at this stage, we're claiming that the other equalizers can be found by specifying a function E such that F equals GE plus such that there is a bijection happening here. But we can simplify this description, because as soon as I have an arbitrary bijection going on here, I can recover the small e by composing this bijection with my given e. So since I'm requiring EFG composed with H to equal small e, the small e can be recovered from the bijection. And moreover, that small e recovered from the bijection, from an arbitrary bijection H, will satisfy F equals G. Why? Because Fe will equal Fe of equalizer of FGH, and we know that F composed with the equalizer of FG equals G composed with the equalizer of FG. And then that equals G. So what I'm trying to say is that I can have an arbitrary bijection here. And then by composing that arbitrary bijection by this map the equalizer of F and G map, forgot the Q there, sorry, I will get a map E that will make F and G equal to each other. Was this clear or was it confusing, Michaela?
No, I think it was clear.
So what I'm trying to do basically is to say that I can build all possible equalizers just by taking a random set E that's bijective to my set EQFG, and then the way I can build an equalizer out of it is just to take a small e to be the composite of H and this one, and it will be all fine.
Yes, yes.
Which now kind of matches with what we said here, that the equalizer of F and G is that set or any set bijective to the one above. This way we'll now describe all possible equalizers of F and G. We'll take a few moments here. Carlisle, step out for a moment and wait for you.
Cool, no problem.
So in general, we will have many equalizers, right? Because you can always find sets that are bijective to a given set.
Yes, yes.
Which will be the case when there will be only one equalizer? Will there be such case ever?
Given that you've asked, I'm inclined to think there is, but I can't. I mean, you could always just rename the elements in your set and you'd end up with a new equalizer, wouldn't you?
Can you always do that? Can you always rename elements in your set and end up with a different one? So we're asking an interesting question, Carlisle. Because sets can have multiple infinite many, in fact, by other sets bijective to it, it seems like equalizers will always be many. Will there be ever a case where equalizer is exactly one in the category of sets?
If this is empty.
Excellent. Does X need to be empty for that?
Well, the equalizer needs to be empty, but oh yes, just the equalizer needs to be empty.
So if I have a set X that's split up in two parts, sorry, no, I don't even need two parts. I have a set X, but F and G are such that they always, no matter what point we pick in X, they always map that point to two different places. This would make EQ of FG empty set, right?
Yes. Yes.
And then here we put the empty set. This is the unique empty function. And now we want to find another equalizer, which will be a set that's bijective to the empty set, but there is only one such set. It's the empty set itself. And there is only one bijection from the empty set to the empty set. And of course, we're using here the fact that the empty set is the initial object. But unlike in a general category where you can have isomorphous copies of the initial object, in the category of sets, the initial object is strictly unique. Unlike the terminal object, which is multiple, terminal objects are the singleton sets. There are many of them, but the initials are unique.
Yeah. So yeah, they don't actually you don't guarantee the unique on either.
No, because remember, if you take the dual of the category of sets, the terminal becomes initial. So that's the example where you have many initials. So it's an oddity of the category of sets that for some FGs, there is indeed exactly one equalizer. It's a very strange phenomenon, and we actually don't care about such phenomenon too much, because we don't care things to be equal in a category. We want the objects, we want them to be isomorphic at best. For the morphisms, we of course want them to be equal, unless we go to two-dimensional category theory, where there are morphisms between morphisms, and then we only want morphisms to be isomorphic.
So sort of as a general question, I've had a lot of trouble in like this abstract algebra when we talk about equality very loosely without ever referring back to equality of sets. It seems to some point we sort of don't even know what we're talking about anymore when we talk about equality. So in like category theory, when we say two morphisms are equal, is that just basic? Like, do we define equality just by the few axioms that we have? Like, is it implicitly defined by just the associativity and identity axioms and stuff? Or how do you make sense of?
Yeah, equality. The term equality still remains its strict meaning. It's just that many concepts will be often defined in terms of being isomorphic, but then it will explicitly say that we will not pretend that they're equal, but actually they're not really equal, but they're isomorphic to each other.
I mean, what is its strict meaning in something where you don't have sets underlying the structure?
Well, you can think of a general category as a set-based structure, right? You got a set of objects, you got a set of arrows, and then equality means that things are the same. But in terms of when I want to prove two arrows are equal in a general category, the only tools I have are associativity axiom and the identity axiom. Okay, so let's look at another example of an equalizer from a different category. An important example. This will be from the category of vector spaces. But one of these two arrows will be a very special one. One of the two arrows that will equalize. So let's consider an example of an equalizer in the category of vector spaces, let's say over real numbers. Let's take the space R cubed, and let's consider two maps to also R cubed. The first one maps a point with coordinates x, y, z to x, y, 0. Maybe, sorry, not that. Maybe it maps to x, y, y. And the second map maps everything to 0. Well, first of all, is this first map a linear map? What do you think? First one indeed looks like a linear map. The second one is also linear, right? Okay. What will be equalizer of these two linear maps? So this is F and this is G.
Kernel F.
That's right. It will be what we call the kernel of F. You're familiar with this concept of kernel, right, Mikhaila?
Yes, yes.
Exactly the kernel of F. It will be those things that are mapped to 0, because the other map maps everything to 0. And we could answer this based on our intuition for sets. It actually works out like this. Equalizers in the category of vector spaces are constructed the same way they're in the sets. You just take the set theoretic equalizer to functions. It happens to be a subspace always. So you can have it as a vector space, and then the inclusion will be linear map. And this phenomenon that in the category of vector spaces, some category theoretic construction works very similar to how it works in the category of sets, is an important phenomenon that's shared by lots of different algebraic structures. For topological structures, however, that is also true, that is still true, but then you have to think how to equip your new structure with topology. It could be challenging sometimes. For topological structures, something a bit more is also true. The dual notion of equalizers, which is co-equalizer, which we still have to see what it is, will have a similar feature that it can build as if we're in the category of sets. But for algebraic structures, that's no longer true. Maybe that's actually what we want to do. Let's look at the dual notion of an equalizer, which is a co-equalizer.
So maybe like the better understand if you develop topological spaces. For example, vector spaces, you can characterize linear maps as those that send all subspaces to subspaces, but logical spaces would be the other way around. We look at the inverse image, is that like what complicates it?
It's kind of related to that phenomenon, but there isn't really, I don't think there is a fulfilling way of formalizing what you're suggesting. So I'm making a remark here, a conceptual remark. The notion of an equalizer seems to capture the notion of kernel, which is an important notion in algebra, and not just for vector spaces, for other structures as well, for instance, groups. But if I really want to fully abstractly capture kernel, I also need to define abstractly what this is. What does it mean for a map to map everything to zero? And the way this can be done is the following. In the category of vector spaces, it turns out that the singleton space, the zero-dimensional space, is both initial and terminal at the same time. In the category of sets, you don't get this, right? Initial objects are the interset, terminal objects are the singletons. But in the category of vector spaces, the singleton space is both initial and terminal. Now, the effect of that is that if I have any two vector spaces x and y, because this is terminal, I have a unique map going there. And because it's initial, I have a unique map going from there to y, which as a composite gives me some special morphism from x to y. It will be called zero morphism and will be denoted by zero. And this map G we had here is actually such a morphism. So we can define zero morphisms in a category where initial object and terminal object coincide, and then we can define kernels in a category by taking equalizer of the zero morphism and any other morphism. Does that make sense, Michaela?
Yes.
And so we will really be able to abstract the notion of kernel to a general category as long as the initial and terminal objects coincide there. Okay. Now, if mathematics before category theory comes on stage has a lot to do with solving problems, right? I mean, even nowadays, that's how mathematics is being portrayed everywhere. We have these open problems that are open since more than 100 years sometimes, and when some progress is made towards solving them, that's what gets printed in the newspapers and so on. The practice of solving these problems has shown that in some cases the problems are so difficult that you need to build an entire theory before you can come back and solve the problem. And this is very well seen with the solution of Fermat's last theorem. There's a whole toolkit of algebraic number theory that was being developed in the 20th century before it came to maturity to be able to solve the problem. And of course, you also need somebody brave and genius enough to apply the toolkit to the problem. And so developing theories becomes then also important because these are like, it's almost like developing technology. And when you develop technology, it's very important to develop the right components. For instance, if we're making computers, it's very important to have a very good technology of make chips, computer chips. And in mathematics, these components are concepts. So it's very important to have well-developed concepts, and that these concepts fit each other nicely, just like the chips should fit different motherboards and so on. And category theory is that area of mathematics for which correct development of concepts comes to the forefront. It is the priority number one, that you have beautiful concepts, so that then they're agile enough to be useful in application. And from that point of view, what we are seeing here is something important, because knowing how kernels are important in various concrete areas of mathematics, this now gives us a hope that we will be able to capture some behavior of these kernels in a very abstract category theoretic setting by this more general notion of the kernel given by an equalizer, of a special kind of an equalizer. Okay, next, let's see what is the dual notion to an equalizer. It's called a co-equalizer. And we're going to explore what it would be in the category of sets. Sorry, adjusting my board just a little bit here. First of all, let's write down the dual diagram. So the diagram for equalizer is this. And dual means apply this definition to the dual category, the opposite category, where all arrows are reversed. And let's do that. So our x and y will now have f and g running in the opposite direction. Equalizer will now be going opposite way. It will be called co-equalizer, co-EQ. And there will be one name for the object as well. And now the condition will be saying that, first of all, this co-EQ FG composed with F equals it composed with G. But also, if I have another morphism E, such that EF equals EG, remember before we had FE equaling GE, because the arrows have reversed, composition also reverses, then there must exist a unique H, now this time going towards E. Are we happy with, Mikhail, are you happy with this being the dual of the definition of equalizer?
Yes, yes.
Great, now let's try to see what it will be, just like we did with the equalizer. Let's take two finite sets into some random functions between them and try to come up with versions of what this could be in that example, and then we abstract from the example to generate a general equalizer. So let's say my two sets are the following. So X has, let's say, 4 elements, and maybe Y has 5 elements, and F maps these elements the way I'm drawing with the orange arrow. And then G maps them the following way. And let us give examples of three arrows going out from X. E1, E2, and E3 as before. Sorry. That will fulfill the requirement that F will equal EG for each subscript under E. So who would like to name the first example? Yes.
So we can at least include the equalizer of y and x, I think. So if you take all those things in y, that gets into the same thing.
So you should tell me what the elements of capital E1 are.
Then I'm not
Sorry?
can we number them then?
Yeah, we can number this. So this is 1, 2, 3, 4. And this could be 1, 2, 3, 4, 5.
So we can take 1, 3.
You want to take 1, 3, and 5. And 5.
So 1 to 1.
You map 1 to 1.
2 to 2.
There is no 2 on the other side.
2 to 3, sorry.
2 to 3.
And 4 to 5.
What do we do with 3?
Starting to think this example won't work.
It won't work.
No, I don't know, I'm not sure.
Okay, let's see. Anything that comes to 1, does it make the
I think it's
I begin with 2 on the side, right?
mm-hmm.
With the blue arrow it maps here, then it maps to 3.
Yeah.
But if I take the orange arrow, it maps to different spots. It doesn't work.
Yeah. Okay, I'll go for the symbol. I'll send everything to the symbol elements.
Okay, so you want to have only one element in here. Let's call it 1, and you want to map everything. I'm not drawing it because there's only one function there, so you map everything to that element. Michaela, would you like to give it a try?
I can't. I can't think of anything at the moment.
Can I give it a try then?
Yes, please.
Okay. Let me see. I'm going to also take some time.
I think I have an idea. So I think if you make E2 a 2 element set, if we call it 1 and 2. And then if you take 1 and 2 from X and map them both to 1. And then 3 and 4 and map it to 2.
Okay, let's see if that works. So we want to compare the composites, right? So we'll do it for every element of Y. Take 1, map it by blue and orange map. They both go to 1, so it will be fine. It will be sent to the same place because they're all the same here. Take 2, it goes to 1 and 2, and they do go to the same spot. Take 3, it goes to, both go to 2, so that's fine. Take 4, they go to 3 and 4, and then they go to the same place indeed. And take 5, and they go to the same place already next, so it's fine. Great, well done. Yeah, that seems to be a map indeed that makes F and G equal each other. Let me come up with an example as well. I'm going to, just like before, Mikhail, if you don't mind, I'm going to copy you a little bit. I'm going to have 3 elements here, 1 and 2, And the third one, 3, where nothing will map to 3. So my map E3 will be defined exactly the same way as yours. I'm not going to draw it, otherwise the drawing will be messy. So E3 of x, of every x, will equal E2 of x. Are you happy with that?
Yes, yes.
Because 3 didn't get used, it's fine. The condition will still hold. Okay. Now let's see which of these 3 potentially is a co-equalizer of f and g. Let's see whether E1 works or not. For E1 to be a co-equalizer, we need, for any other E, to have, from the codomain, we need a unique map going which direction? I forgot now.
1 to E1 to.
Yeah. So we need a unique map going this way. If E1 is to be a co-equalizer, there needs to be a unique map going from E1 to E2, making the triangle commutative. Does it work? Is there such a map? We only have one element in capital E1, so number 1 has to map either to 1 or 2. If it maps to 1, then number 1 here goes to 1, goes to 1. That's fine. Number 2 goes to 1, goes to 1. That's also fine. Number 3 goes to 1. Oops, now it goes to 2. It should go to the same spot. Sorry, it doesn't go to 2. It goes to 2 this way, but that way it goes to 1. And 1 will be mapped to 1 here. 1 and 2 don't match. Do you agree with that, Michaela?
Yes, yes.
So we can't map 1 to 1. Can we map 1 to 2? Also, we can't do that, because if I now map 1 to 2 here, then I would run with a similar problem. With which element? Let's see. The one maybe that goes to 1 there. So 1 goes to 1 there. This will have to be mapped here, but I want that to be mapped here. And so it's a mismatch there. So the map H can't be defined. There does not exist any H. Okay, so E1 is not an equalizer. What about my E3? Is that an equalizer maybe?
We can send E3 anything.
So let's test it with E1 first. With E1, there's only one way to map things, right? Because there's a singleton there. And of course, this composite will equal that, since it's a singleton there. It's a terminal object. Any 2 arrows going from X to there will equal. So that's fine. So it works for E1. Does it work for E2? I would probably have to send 1 and 2 to 1 and 2 here, right?
Yeah.
And then where do I send 3? Well, I have 2 choices. And both of them would work. And that's a problem, because I want a unique H. Do you agree with that, Michaela?
Yes, I do.
I'll get 2 different H's depending on where I have 3. So my selection is not an equalizer either. And now we can try to prove that Michaela's one is a co-equalizer. Sorry, I meant to say co-equalizer. Is a co-equalizer, but let's prove it then for the general case. So if I have an arbitrary function E, how will I prove that there will be a unique H here? The only thing I know about my function is that EF equals EG. So now I pick an arbitrary element in. Do I want the function going that way or the other way? No, I want it the other way, right?
Yeah.
So I take H, I have 2 elements there, 1 and 2. So I need to define what is the value. I take H of 1. What should H of 1 be? I want the triangle to commute, and there are two things going into one, right? These two, right? So I want this going to one, and wherever that one goes, it should be the same spot where the one goes, right? So I actually do want this to equal E of 1, right? But for the same reason, I also want it to equal to E of 2. Do you agree with that, Michaela?
Yes.
But how do we know that E of 1 and E2 of 2 are equal to each other? They might not be equal to each other, then we have a problem, because then we can't build H like before.
Because 2 and 1 gets sent to 1 and 2.
Because E of 1 equals E of F of 2, and because we know that equals E of G of 2, where G of 2 is 2, we can see that E of 1 actually is equal to E of 2. All good?
Yes.
And then I've now not just decided, but also I was forced to map 1 that way. There's only one choice for 1. And what about for 2? H of 2, for similar reasons, it would probably have to be the same as E of 3, right? Because 3 needs to go there, and then 2 needs to go, wherever it goes, it needs to go the same place where E takes it. So it has to be the same as E of 3, and that probably has to be equal to E of 4. And indeed it's equal because of 4 here, which by F maps to 1 and by G maps to the other. And I suspect now, Michaela, that you knew all of this, and that's why you selected E2 the way that you did.
Beg your pardon? Sorry?
I suspect that you already saw all of these things. That's why you selected E2 the way you did.
Yes.
Okay, great. But then let's ask the same question as you asked before. How did you actually select, or how can we abstract from here? What will be the abstraction? Do we see it already, or do we need to work a bit more on this?
Just in the category of sets, at least. I think it will be some sort of equivalence relation, so like a transitive thereof.
Yeah. So abstracting this, what we notice is that if I have two elements that by one function something is mapped to one element and the other function maps the same thing to another one. If I have a situation like this, I absolutely want these two to be mapped to the same place by the coequalizer. Do you agree with that, Mikhail?
Yes, I do.
Okay, so there is some sort of kind of, as you said, equivalence relation going on here, right? I almost want to quotient out by making these two equal to each other. But a funny situation may arise where there is yet another point here, which by F maps to that specific one that G was mapping the other one to, and by G maps to yet another one. And then I would want those two also to go to the same spot. So eventually I would want all of these that are connected to each other by a zigzag like this to go to the same spot. So abstracting from this, then, we conjecture that the coequalizer of F and G needs to be quotient of the set X, so this is our set X, set Y, quotient of the set X by the equivalence relation that's generated. I mean, if I'm deciding to map things to the same spot, then this has to be an equivalence relation, right? Because if two things are mapped to the same spot, then in reverse, they're also, and transitivity also should fall there. So quotiented out by the smallest equivalence relation such that the set of pairs Fy, Gy, these are the, if this is my small y, these are exactly the kind of things I was looking at the beginning, right? Such that this set, where y is in y, is inside E. Are you happy with that, Michaela?
Yes. Yes.
So this is a conjecture. And the homework for today's lecture is to prove this conjecture. Prove the conjecture above. That's the first part. And the second part is to describe all co-equalizers, which would be very similar to what we did with equalizers, where we just took things after bijection.
Specifically in the category of sets.
Yeah. So it's interesting that the equalizer seems to separate some fragment of the set, the fragment where the two maps are equal. It cuts something out, whereas co-equalizer sticks things together. So we now see from this perspective of category theory that cutting something out and sticking things together are dual constructions. And that's going to have a fundamental role in applications of category theory. I want to show you an application in topology here. It will be just an outline, not a full theory. How do we build a Möbius strip? If I want to describe a Möbius strip parametrically, it's complicated equations. There is an easy way to build it using co-products and co-equalizers. Begin with an ordinary strip. And then consider its co-product with just give me a moment, I want to rephrase something I know in the language of co-equalizers only. Yeah, I think in this case it's actually quite simple. I don't need co-products, just co-equalizers will be enough. So take the unit interval 0, 1 and map it continuously to the strip in two different ways. One, map it this way, the way that arrow shows. So start here and here, and it maps in the directional arrow. The other, so that will be one map F. The other, map it opposite way. So let's say this is going to be G of 1 and this is G of 0, and in the first case this is F of 0, and that is f of 1. And everything in between will map continuously in the way that's suggested by the error. What is going to be the co-equalizer? The set that we built here, this one, it's the set of pairs fy, gy, right? Let's identify those pairs. So we pick a random point here, right? The fy there will be here, and the g will be there. And those two need to get stuck to each other. So if I bring them closer so I can see what gets stuck to what, first I need to look at this picture. Right? But now, this will have to get stuck with that, that with that, that with that, and so on, right? Which I can display in a more convenient way by first twisting one of the ends. Did I twist too much?
Yeah, I think so.
Yeah. And then I can say, it's like this. And of course, the thing we will get will be exactly a Möbius strip. But I'm worried that I twisted it too much.
No, it's
Okay. Are you okay with this, Nicola?
Is it supposed to have two twists, like one full twist, or like a one?
Yeah, that's also what I was worried about.
Because isn't the idea with the Möbius strip that you can start and sort of traverse the whole surface without crossing an edge?
But you can do that.
I think my drawing could be simplified to show that it's only one twist. Let me try to do that. So this is what I meant.
No, but that's not good.
That's not good.
I think if you go back to the previous one, you can trace out the path to show that it is.
Yeah, so if I connect this just like this, do you agree? Then in this case, Michaela, there is no twist at all.
Yes, I do.
So I actually didn't do the twisting yet.
Okay.
Still need to do it.
Yeah.
One gradual twist.
Okay, so what is the usual drawing? So the usual drawing would be like this, right? No.
I think it's if you want these this to be one edge.
Yeah.
So if you
Right.
that.
Wait, now what is connected with what? I don't think you should put your hand on the screen.
So now if you start on this, you start here, you go under, come over again and come back to this.
Your picture is still. Oh yeah, yeah. Okay, I like your picture. But for some reason I'm struggling to see how I can transform my picture into yours.
No, I also can't see it.
Maybe we follow your idea. So if I follow the one edge here, I follow one edge, it goes this way, it goes this way, then it goes this way, goes this way, and it comes back. I think this is convincing, right? Okay.
Yes, yeah.
Okay, great, thanks. Now,
I'm still.
so the idea is that the equalizer is going to be this, but how does this help? I mean, this is just sets. The magic here is that we could have been working here in the category of topological spaces, and then not the equalizer, the co-equalizer, and then the co-equalizer would have had topology. We need to still figure out what is the topology of the co-equalizer in general and apply in this case. But it will indeed turn out to be so that this thing as a topological space, not just only as a set, but even as a topological space, will be a co-equalizer of these two continuous maps.
Would you, to induce a topology, would you, this two elements are related, would you share their element?
The way you will induce a topology will be the minimal way in a sense. So you want this universal property that for any other map that is unique, this one, right? You always want these to be continuous. So you want something here to be open if its inverse image here is open. And this turns out to be sufficient. So it's a very convenient way of describing complicated topological spaces, at least the ones that algebraic topology wants to study. And so co-equalizers then become a tool for building and working with spaces in algebraic topology. In this example, we had a bit primitive scenario where we don't really have these transitive chains like we did before. These 2 points are going to get stuck to each other, and then the only two that get stuck to that. There is nothing else. So the equivalence relation that we were generating here is going to be quite simple. It's just going to be this set, union with its opposite, where we turn around the order pairs, union with the diagonal, everything is related to itself. Okay, now the equalizers and the products. This is kind of synopsis of what comes next. Sorry. All right, my paint is not responding anymore. Okay, there we go. Equalizers and products are two special types of limits. I've been using the word limit a few times now without defining them yet. It turns out, however, that any limit can be built using just equalizers and products. So I can now make a little more progress towards telling you what a limit is. Think of a limit as an iterated combination of equalizers and products. And here is one example of combination one can do. It's called a pullback, and we will end off here. So if I have a diagram like this, sorry, if I've got a diagram like this, I could first consider the product of x and y along with the projection maps, and then consider these two composites, f pi 1 and g pi 2, and take their equalizer. So equalizer of f pi 1 and g pi 2. And the resulting object will have a very interesting universal property relative to the initial wedge type of diagram we started with. So there are now two canonical maps from here to x and to y. So the first one is obtained by composing the equalizer with pi 1, and the second one is obtained by composing the equalizer with pi 2. These two maps, let's call them P1 and P2, satisfy the fact that f P1 equals g P2. Why is that? Well, P1 decomposes into equalizer with pi 1 and f, and then it ends up reducing to the fact that this equalizer equalizes f pi 1 and g pi 2. And moreover, if I have another object, Q, with two maps Q1 and Q2, satisfying the same condition that f Q1 equals GQ2, it will turn out that there is a unique morphism this way, unique H, such that the two triangles, this time there are two triangles, Q1 with P1 and Q2 with P2, such that P2H equals Q2 and P1H equals Q1. And just a kind of brief argument, but we will go more in depth in this later on. So why will there be unique H? Well, first of all, because I've got Q1 and Q2, by the universal property of the product, there will be something going into the product. And then that product will turn out to equalize f pi 1 and g pi 2. By the property of equalizer, there will be unique map going here. So this unique map can be constructed as two steps out of the two unique maps coming from the product and from the equalizer.
Is everything here the pullback?
No. So then this thing is called the pullback of the original orange wedge to start with.
Okay.
And even more generally, if you've got a complicated diagram, instead of a wedge, you've got a very complicated diagram here with objects and arrows between them. And these arrows could be going all over the place. The limit of such a diagram is a single object with arrows descending to every single node in the diagram below, which has the universal property that for any other object, but now these triangles that arise here must be commutative. And the property is that if I have any other cone like this with all the triangles that arise there, like for instance this triangle going here and then there being equal to that, the arrow is
so when you say all the triangles, is that all the triangles with two blue sides or all?
Yeah, all the triangles with two blue sides, which will originally the static diagram doesn't have to be committed. So for any other orange one, there must exist a unique. There exists a unique H, and we can build this blue thing that's called the limit of the diagram. It turns out we can always build it by a combination of products and equalizers. So limits and the corresponding dual motion of colimit, they are the basic operations we perform inside a category. When we can. Not every category will have all sorts of limits. Some categories lack some limits.